We will get started today by quickly recapping what we did last time. So we defined what is central force motion. Basically, it is the motion in any force field which depends only on the absolute magnitude of the distance of the particle from a specific point, usually chosen as the origin. The force and hence the potential has no dependence on any of the angular parameters like theta or phi. Okay. All right. So we discussed that for example, in the classical mechanics analog, you clearly know that in such a situation, angular momentum is a conserved quantity, right? Because there is no torques acting on the system. So in quantum mechanics, the equivalent statement is that the angular momentum operator commutes with the Hamiltonian. Okay. So this is what we will try and understand a little bit more today. We will actually explicitly do the calculation and show that the angular momentum commutes with the Hamiltonian, and we will also learn a little bit about what are vector operators in quantum mechanics. Okay, so this is where we were. We wrote down the definition of angular momentum, which is x cross p in classical mechanics. We promoted the x and p to operators in quantum mechanics and wrote down the corresponding operator in quantum mechanics, the L hat operator in quantum mechanics. And then, just 1 minute. So we defined things in terms of the Levi-Civita symbol epsilon ijk instead of working with the explicit cross product every time, because as you will see, the use of the epsilon symbol simplifies our calculation somewhat. And then we wrote down the Lx operator, the L1 operator in our notation as an example, which is basically x2 ddx3 minus x3 ddx2, which is an operator. So I should also mention that I'm writing everything explicitly in terms of position space. So these are the position space operators, which is what angular momentum is usually written down. Okay, so let us continue. So what is it that we want to understand? So the way we set up the problem is by claiming that it is very useful in quantum mechanics to, before we start solving the problem, it's very useful to collect all the operators that commute and figure out the common eigensolutions, eigenstates of all these operators. The reason being that if you write down the common set of eigensolutions of all these operators, then the action of operators on these eigenfunctions become trivial, right? So now, by definition, an eigenfunction is something that an operator acts on the eigenfunction to give you the same eigenfunction back up to a multiplicative constant called the eigenvalue. So this is where we were. Okay, so let me start by writing down Li, which is minus I h bar epsilon ijk xj dd xk, and this is an operator. Sometimes I will miss writing the cap on the operator, simply because I also have to write down the vector symbol and so on and so forth. Okay, so I will have to first demonstrate that this operator does commute with the Hamiltonian. And some of you might have seen this already, but I'm assuming that many might not also have seen this, particularly in the symbolic notation here. So I will do it in steps very slowly. So in case it is extremely simple for you, please bear with me for some time. Okay, so remember that the Hamiltonian for this problem is composed of the del square operator and the potential V of R. So ultimately, we want to understand how L commutes or doesn't commute with the del operator and something that depends only on position. So let us take it step by step. So let us first try to understand. And remember that the L operator itself is composed of x and the differential operator ddx. So we'll have to understand how all these guys commute or don't commute with each other. So the first part is very simple. So let us begin by calculating the commutator of x and ddx. So let us compute x in the commutator, ddx in one direction I, and x in another direction j. Okay. How will you do it? Always, when you want to compute a commutator, you multiply it with some test function f. Okay, and this is equal to ddxi xjf minus xj ddxif The first term can be written in terms of two simple terms. ddxi first acts on xj with f treated as a constant, and ddxi acts on f with xj treated as a constant. So this is f dxj dxi plus xj df dxi minus xj df dxi. And you see that this and this easily cancel with each other, leaving you with f times the differential of xj with xi. And remember that xj is x1, x2, x3, and xi is also x1, x2, x3. And this is equal to 0 if j is not equal to I, because you know that x, y, z are independent variables. So dx, dy is 0, dy, dz is 0, and so on and so forth. But if j is equal to I, dx, dx is 1. So this is equal to f times delta ij. So you can now take off the arbitrary test function f on both sides of this equation and write this commutator as an operator equation. The commutator of ddxi with xj is equal to delta ij. This is simply the statement that the differential operator and the position operator commute if we are talking about different directions, or they don't commute if we are talking about the operators in the same direction. Okay. All right. So given that we know what this is, now let us actually go ahead and calculate the commutator of the angular momentum with x and with ddx both. So what is the commutator of angular momentum in one direction Li with x in the other direction, in some other direction xj? I could be equal to j, or I need not be equal to j. This is equal to minus ih bar epsilon ijk xj ddxk. Sorry, I should not use the same ijk, so I should be careful. So when you do symbolic notations, this is something you have to be careful. So I'll use epsilon ilm xl ddxm comma xj. Okay, at any point, if you have any questions about anything that I'm writing, please stop me and I'll clarify. So this is effectively equivalent to h bar and the epsilons are constant, so I can pull them out with impunity. So epsilon ilm, the commutator of xl ddxm with xj. Okay, and the way you evaluate this is by realizing that the x parts commute, right? Because xl and xj commute. I can talk about the positions in different directions and there is no commutation relations between them. So for the purposes of this commutator, I might as well pull out the xl part from the first guy. So I can write this as ilm xl, the commutator of ddxm and xj. And we have just now shown that the commutator of differential operator and the position operator is delta ij. So this part would be equal to, excuse me, delta jm. Okay. So if I put everything together, this becomes minus ih bar epsilon ilm xl delta jm. Okay. And what is this? The delta function forces the m value to be equal to the j value. So I have, this is equal to minus ih bar epsilon I j m xm. Okay. Now, if I switch the indices j and m, I have to take a minus sign because the epsilon is antisymmetric under every index, right? So remember that epsilon I j m is equal to minus epsilon. Sorry, this is still L. I made a mistake here, forgive me. So this is equal to minus ih bar. The delta function forces the m to be equal to j, so this is equal to ilj xl. Okay. And now I will switch the L and the J in the epsilon. So epsilon ILJ is equal to minus epsilon IJL So this is equal to minus epsilon and plus, minus and plus here becomes plus I J L X L. Okay, remember that the L here is summed over. Okay, any repeated index is summed over. So ultimately we have the commutation relation, the commutator of xi with Li with xj equals IH bar epsilon ijk xk. Okay. Oh, don't worry that I switched symbols here. Since the index is summed over, it really doesn't matter if I call this index L or K or M or whatever it is that you want. So the commutator of the angular momentum operator with the position operator takes this particular form. Okay, this is an important equation. So let me box this equation. And if you follow these exact same steps and compute the, the commutator of Li with ddxj, you would actually find that this is equal to IH bar epsilon ijk ddxk. I'll box this in blue, which means you have to verify this equation. Take it as an assignment. Okay. So notice that you see a pattern emerging here. The commutator of Li with xj depends only on x, and the commutator of Li with ddx only depends on ddx. In other words, Li, the commutator of Li with xj mixes all the x components together, and the commutator of Li with ddx mixes the components of the operator ddx with each other. Okay, so this is an important statement, and this is actually true for any vector operator. Okay, so suppose if you have a vector operator, suppose you have a vector operator which can be written as V equals some Vx operator times I, or I will not use this Cartesian notation, vector operator with components V1, V2, V3. Okay. Then it is always true that the commutator of Li with any one component of this vector operator will give you IH bar times epsilon ijk vk. It will mix the components of the vector operator together. Okay. So I can turn this argument around and claim that this is the very definition of what is called a vector operator in quantum mechanics. So how will I distinguish between a vector operator and three operators that I write together? So suppose if I have three distinct operators and I write them as A1, A2, and A3. Okay. And then I suppose somebody claims that this is not just A1, A2, A3, but these are the three components of a vector operator A. Now, how will I be able to check in quantum mechanics if this statement is actually correct? The way I will check if this statement is actually correct is I will calculate the commutator of the angular momentum operator with any one of these components and check to see if I get something like the right-hand side of this equation. In other words, the commutator of the angular momentum operator with the components of a vector operator always mixes the vector operator, components of the vector operator together. This is not very mysterious. This also happens in classical mechanics for any vector. So suppose if you take an angular momentum, and if you take a vector and you rotate the vector, which is what the action of angular momentum in quantum mechanics actually is. If you rotate the vector, then the new vector has x component and y component that are functions of the old x component and y component. In other words, in classical mechanics, for example, right? Suppose, sorry, this has stopped showing again. Forgive me. Okay. So in classical mechanics, if I have, if you write down some Cartesian coordinate system, this is my x-axis and this is my y-axis, and if I write down any vector, right, and I call this vector some v, and this vector has components vx and vy, and suppose I rotate this vector by some angle theta, and I get a new vector over here, which is v prime, which is related to v by some rotation theta, then you know that the components of the new vector equals cosine theta, sine theta, minus sine theta, cosine theta times vx, vy. In other words, the new components of the vector are a linear combination of the old components. That is exactly what the equation above, boxed equation above in quantum mechanics is also telling you. It tells you that the commutator of Li with Vj basically mixes the components of the vector operators together. Okay. Next semester, when we actually study the theory of angular momentum, I'll talk more about what this commutator means and the difference between finite and infinitesimal rotations. Anyway, so for the purposes of quantum 1, for now, you can simply take this as the statement of what a vector operator really means. All right. So this is how L commutes with a vector. So how does L commute with a scalar? So as an example of a scalar, let us take the absolute square of a vector, right? So suppose if I take b square, which is in summation notation, this is equal to Vj, Vj, right? So this is V1 square. So this is equal to V1 square plus V2 square plus V3 square. So let us calculate how, and so what is a scalar? In classical mechanics, what is the corresponding statement? A scalar is just a number in classical mechanics, right? And rotating a coordinate system doesn't do anything to a number. So in this particular example that we chose, the example of a scalar is the length of this vector. And under rotation, the length of a vector doesn't change. Okay, so which imposes the constraint that this matrix that you have is an orthogonal matrix. Anyway, so in quantum mechanics, you have a corresponding class of operators called scalar operators. Scalar operators are those operators that commute with Li. Li has no change on what a scalar operator does. So let us actually verify this statement also by calculating the commutator of Li with V square. This is equal to the commutator of Li with Vj, Vj. And by applying the rules of commutation, I can pull out one factor of Vj on the left and write this as Vj times Li Vj. And I can pull out one factor of Vj on the right and write this as Li Vj, Vj. Okay. So I hope this is clear to everybody. If there's any questions, please ask. Now I have already calculated what the commutator of Li with a vector operator is. We already know that this particular quantity is equal to IH bar epsilon ijk Vk. And this is also exactly the same. So I can write this as, now I should be careful with the ordering. I should not mix up Vj and Vk. So in the first term, Vj is on the left. I'll pull out the IH bar epsilon ijk because that's just a number. The first term is Vj Vk. And the second term would be, here the Vk would appear first, the Vj would appear second. Okay. Now if you look at this equation, you realize that epsilon ijk is antisymmetric in jk, and Vj Vk plus Vk Vj is symmetric in jk. Okay, which means if you multiply something that is antisymmetric in two indices with something that is symmetric under the two indices, the product of these two guys gives identically 0. So we can say that Li with the scalar operator v square is identically equal to 0. But 0 came out funny, so I'll write 0. Okay, this is also an important equation. The corresponding statement in classical mechanics is that rotation doesn't change the length, where length is a scalar quantity. And in quantum mechanics, the statement is that the components of the angular momentum operator commute with a scalar operator. So this defines what a scalar operator is for you. So a vector operator is one whose components are mixed by the angular momentum operator, and a scalar operator is one which is left unchanged under rotations in quantum mechanics. So with this information, we can now, excuse me. With this information, we can now proceed to understand if the Hamiltonian is symmetric under invariant under rotations or not. So what about the Hamiltonian? Can you explain how the length being constant pulls the constraint that rotation matrix must be orthogonal? Okay. Aside. Okay. So the question is, can you explain how the length of the vector being constant puts the constraint that the rotation matrix must be orthogonal? So consider a vector in classical mechanics. So let us say you have a vector, okay, with components v1 and v2. Okay, and then I rotate the vector, and the vector becomes a new vector, which I can write as some rotation matrix times the old vector. So in this particular example, this 2 by 2 matrix is a rotation matrix. If I do it in 3 dimensions, it will be a 3 by 3 matrix, which is a rotation matrix. So whatever be the number of dimensions, there is always the relation, the symbolic relation that the new vector is the rotation matrix times the old vector. Okay. So what is the length of the vector before rotation? Let's call this L, and this is basically equal to V transpose V, right? Because V transpose V is V1 V2 times V1 V2, which is V1 square plus V2 square. Okay, this is the length square. So what is the length after rotation? The length after rotation is V prime transpose V prime. But V prime transpose is basically V transpose times R prime transpose from this equation. Yes. So I can write this equation as V transpose R transpose times V prime is R times V. So I can write this equation as V transpose R transpose R times V. If this has to be the same as V transpose V, then whatever that is multiplying V transpose V inside has to be equal to the identity matrix 1. So this implies that R transpose R equals 1. Okay. So matrices that obey the rule that the transpose times the matrix itself is 1 are called orthogonal matrices. Okay. All right. So let me draw a line here. Okay. So let's get. So we have demonstrated that Li commutator with the components of a vector operator mixes the vector operator, and Li leaves the scalar operator alone. So Hamiltonian is composed of two different kinds of operators. The first operator is minus h bar square over 2m times del square plus V of r. Okay. But the first part I've already shown, because del square operator is del dot del. This is a scalar operator. Even though Hamiltonian does not commute with del, it does commute with del square. Because del square is a scale, even though Li doesn't commute with del, it does commute with del square because del square is a scalar operator by this logic. Li v square is equal to 0. So the first part is okay. So I have to show you what the second part is. So I have to prove to you that Li, the commutator of Li, with some function that depends only on distance, we have to show that this is equal to 0. If we can show that this is equal to 0, then we are in business. Then we can claim that the angular momentum indeed commutes with the Hamiltonian, and then it makes sense for us to look for common eigenfunctions of the Hamiltonian and one of the Li operators and the L square operator, because the L square operator also commutes with the Hamiltonian. Okay. So how do you calculate this? So this is some operator that depends only on the distance. So let us multiply this with some test function psi. So this is equal to IH bar epsilon ijk xj ddxk comma f of r acting on psi. Okay. So I'll pull out the IH bar epsilon ijk, and this is the commutator of xj ddxk comma f of r acting on psi. Again, please stop me if you have any questions. So I'll write this down explicitly. This is equal to xj ddxk acting on f of r times psi minus f of r xj ddxk acting on psi. Again, the first term can be written as xj. The first term is psi d f of r dxk. The second term is plus xj f of r d psi dxk. The third term is minus f of r xj d psi dxk. And notice that the second term and the third term will cancel even though the x and fr are in different places, because since f is only a function of the absolute distance, it commutes with any position because it's a function of position alone. So this part and this part cancel, and I am left with IH bar epsilon ijk xj df dxk times psi. Okay, I'm going to pull psi out because it is just a test function and it commutes with any function of distance again. Okay, so the commutator of Li and f is thus equal to IH bar epsilon ijk x times df dxk. So we have to understand what is df dxk. F of r. Now what is r? So r is equal to square root of x1 square plus x2 square plus x3 square. Okay, so which tells me that if I take the derivative of f with any one x, let us say df by dx1, what do I get? I'll first have to differentiate f. So this is d dx1 of f that only depends on square root of x1 square plus x2 square plus x3 square. Right? Does this make sense? So I can write this as dr dx1 df dr. Okay, so this is df dr, and dr dx1 is r is this guy, so I have to do this is 2x1 divided by excuse me, square root 2 times square root of x1 square plus x2 square plus x3 square. So df dx1 would be equal to x1 over r df dr. Does this make sense to everybody? Which means that IH bar epsilon ijk xj df dxk would be equal to IH bar epsilon ijk xj df dxk would be xk over r df dr. And again, I will use the same logic that this quantity xj, xk is symmetric in j and k, and this quantity is antisymmetric in j and k. And so a multiplication of a symmetric tensor and an antisymmetric tensor is identically equal to 0. So thus you can also show that Li commutes with any function that is only a function of the absolute distance. Okay, so since Li commutes with del square because it's a scalar operator, and Li commutes with any function v of r where it only depends on r and not on the angles, we can conclude that for a central force problem, we have H Li commutated with the Hamiltonian is identically equal to 0. And we also know that also Li L square is also equal to 0 since Li commutes with any scalar and L square is also a scalar. Okay. So which means that in this particular problem, we can look for the common eigenfunctions of, see, I takes on I, J, and K. There is 3 values. Now the other question is, can I take the common eigenfunctions of all Li's and H and L square? In other words, can I take L1, L2, L3, H, and L square? And that you will actually see that it is not possible because Li itself is a vector operator. And for any vector operator, as we have seen, Li with any vector operator Vj equals IH bar epsilon Ijk Vk, right? And since L itself is a vector operator, this commutation relation applies to L also. So I can put Vj equal to Lj in this equation, and I get the commutator of Li and Lj, and this is equal to IH bar epsilon Ijk Lk. In other words, the different components of L do not commute with each other. Okay, even though Li commutes with Li, Li doesn't commute with a different Lj. So the different components of the angular momentum operator do not commute, and they form this particular very nice relation between them. And as we will see in the next semester, this is an example of what is called Lie algebra in group theory. And Li's are called the generators of orbital angular momentum. We will not use these terminology in this particular course, but we will introduce them in quantum 2. So the different components of Li do not commute with each other, but I can pick any one of the 3 Li. So let us usually, the goal is to pick L3. Even though there is no reason to pick L3, we can as well pick L1 or L2. And the convention is that you pick L3. In terms of the differential operator notation, L3 has a very simple eigenvalue equation, as you will see in a second. So the goal of solving any central force problem in quantum mechanics thus becomes look for simultaneous eigenfunctions of H, L square, and L3, or H, L square, and LZ, LZ, whatever you want to go. Okay, so this is what we want to do. Again, I cannot find the simultaneous eigenfunctions of H, L square, L1, L2, and L3 because the different components of angular momentum L1, L2, L3 do not compute. Okay. All right. So before proceeding, let me remind you that in terms of the spherical polar coordinates, you have to be able to write down the form of L1, L2, L3, and L square. And this is important if you want to solve the differential equations. So spherical polar coordinates. In spherical polar coordinates, X is R sine theta cosine phi. X2 is R sine theta sine phi. And X3, which is Z, is R cosine theta. And you can verify that X1 square plus X2 square plus X3 square is just R square. So we have to understand what is L1, L2, and L3 in this set. And doing this is not very easy. It's a little messy because you have to calculate all the differentials. But at the end, the formulas themselves are pretty simple. So let us actually give one example. If you change the coordinates like this, how do the differentials change? Suppose if I calculate suppose if I have ddx1, then I have to be able to write ddx1 in terms of r, theta, and phi, because x1 can change because r changes, or theta changes, or phi changes, because x1 is a function of all three coordinates. Similarly, ddx2 would be a function of ddr, dd theta, and dd phi. Okay? In general. So we have to be able to understand how these changes occur. So the way you calculate it is by applying the chain rule of differentiation. So ddx1 would be equal to dr dx1 times ddr plus d theta dx1 times dd theta plus d phi dx1 times dd phi. Okay, the first part tells you how much x1 changes because of a change in r. The second part tells you how much x1 changes because of a change in theta. The third part for phi. By the way, the inverse is also true. Suppose if I go from r theta phi to x1, x2, x3, I can say that, for example, dd phi would be because dxi, d phi, ddxi. Okay, in shorthand notation, this is dx1 d phi ddx1 plus dx2 d phi ddx2, and so on and so forth. So if I expand this out, let us actually expand this out and calculate it just for some little bit of practice. What is this equal to? dxi over d phi. dx1 over d phi would give me minus r sine theta sine phi ddx1. dx2 d phi would give me plus r sine theta cosine phi ddx2, and dx3 d phi would be 0 because x3 is not a function of phi. So if I write this, I realize that r sine theta sine phi is just x2, so I can write this as minus x2 ddx1. R sine theta cosine phi is just x1, so plus x1 ddx2. And you can realize very quickly that the right hand side can be written as I over h bar times L3. Okay. So you can quickly prove using the relation L3 equals IH bar epsilon 3 JK xj dd xk. You can prove that x3 is given by x2 ddx1 minus x1 ddx2, which tells me that in this spherical polar coordinates, L3 takes the very simple form. What is this? H bar over I is minus IH bar dd phi. Okay. So L3 has to do with rotation with respect to the angle phi. Okay. Similarly, you can figure out what is L1 and L2. L1 and L2 will not be so straightforward. They'll depend on both theta and phi. Okay. They will not depend on R. Sorry. So here I should actually be careful. So dr dx1 is this term would not be there. Forgive me. Simply because when I rotate, I'm not changing R, right? I'm just fixing R and then sweeping over the angles theta and phi. So I made a mistake here. The first term will not be there. It's only a function of theta and phi. Okay. All right. So for completeness, let me write down what L1 and L2 are based on my calculations, and please verify these: sine phi dd theta, or you can just look it up in any book because these are all pretty standard formulae. And L2 would be equal to IH bar minus cosine phi dd theta plus cotangent theta sine phi dd phi. Okay. So what is the L square operator? L square operator would be, now we can go ahead in these terms and simply calculate L1 square plus L2 square plus L3 square and write down what is L square operator. L square operator is basically minus h bar square times 1 over sine theta d d theta plus 1 over sine square theta d square d theta square. Sorry, d phi square. But I want to write down the L square operator in a slightly different form. So again, verify. If you're too bored to verify all three, at least verify one of them. At least it will give you some practice in working with differentials. So notice that L square can be written as Li, okay, which is IH bar epsilon ijk xj dd xk. Now I have to multiply this with itself. So I have to multiply this with IH bar. Now this is I, so the first letter is I, but I should be careful. I should not use the same symbols to sum over because J and K are dummy indices. They are summed over. So let me use a different set of indices, ILM, XL, DD, XM. Okay. So this might be something that you're not familiar with. So please stop me if there's any questions. So there's two factors of IH bar. So this is minus H bar. Then I have this curious combination of Levi-Civita symbols, ijk times ILM, xj, dd, xk, xl, dd, xm. Okay. Now this product of epsilons can be written in terms of delta functions. Epsilon ijk times epsilon ILM. What can this be equal to? Let us think about this for a second. So for both these epsilons, the first symbol is I, okay, that is fixed. And J and K can be either any of the other two directions. Let us say I is 1, which means J and K have to be either 2 or 3. Because J and K can now not be equal to I, because if either one of them is equal to I, this is equal to 0 because epsilon cannot have two indices that are the same. So J and K are the two other orthogonal directions. That part is fixed. Of course, we only have 3 directions to choose from and one of the directions is fixed. So J can be either the 2 direction or the 3 directions. So which means, and similarly, L has to be the 2 direction or the 3 direction, which means J, the direction of J is the same as direction L and the direction K is the same as direction M. That is one possibility. Or the direction J is equal to direction M and the direction K is equal to direction L. That is the other possibility. So this can only have 2 particular terms. The first term is J equals L and K equals M. The second possibility is J equal to M and K equal to L. Okay. Oh, again, my thing has stopped showing. Okay. And between these, there'll be a relative negative sign because if I switch the indices L and M, you will actually see that they have to be antisymmetric. Anyway, so this is a combination of 2 delta functions. So my L square operator can thus be written as minus H bar square times delta JL delta KM minus delta JM delta KL times XJ ddxk. Remember that x and ddx don't commute, so you should not switch the orders inside the bracket for now. Okay. Now I'll leave it to you as a homework, and I will actually also upload the proof of this in case you have a difficulty. You can actually show that the sum over J, where this J is assumed to be summed over, this particular combination xj ddxk times xj dd Okay, so sorry, let me do one more step and then give you the answer. So L square is minus h bar square. I'll keep everything in terms of j and k. So the first term is xj ddxk, and the delta function forces L to be the same as j and m to be the same as k. So the first term is xj ddxk, and the second term is xj ddxk times this second delta function forces L to be k and m to be j. So you get xk ddxj. This is your L square operator. Okay. And when all is said and done, it turns out that you can write this L square operator as minus h bar square. So I'll write this in blue because I've not proved it. Minus h bar square r square del square minus r ddr ddr of r square ddr. Okay. I strongly encourage you to show this because this is a very important relation, and this actually helps us rewrite our Hamiltonian in terms of the L square operator. So again, if you are not able to show this, I will upload a small note as part of this start of the lecture notes today later, where I will show that the line before leads the blue line below, which means that I can write my del square operator. If I rearrange this blue equation, I can write my del square operator as 1 over r square ddr r square ddr minus L square divided by h bar square r square. And since Hamiltonian is 1 over 2m del square, for the central force problem, I can write the Schrodinger's equation h psi equal to E psi as minus h bar square over 2 mu r square ddr r square d psi dr plus 1 over 2 mu r square L square psi of r, just psi, plus V of r psi equals E psi. This is my time independent Schrodinger equation for the central force problem, where I have written everything in terms of the operator DDR and the operator L square. Now, why do I go to all this difficulty to rewrite a very simple looking Hamiltonian? The reason I've written this down in this particular fashion is because this differential equation, even though it looks more complicated than just del square equal to E psi, is simpler to work with because I have now separated the differential operation into two terms. The first term here you see only depends on the r coordinate, and all the angular changes is incorporated in the L square operator. The third term V of r again has no information about the angle because it is a function of distance alone. Okay, so I can now proceed to solve this differential equation by claiming that if I know the spectrum of L square, I know everything about the angular dependence of psi. And once I know everything about the angular dependence of psi, I can use a simple separable solution method to figure out the radial or how psi depends on r, the radial coordinate r. So this is the strategy we will employ, but we will continue with this equation and its solution on Wednesday. But this is the reason why we go through all this trouble to write everything in terms of the angular momentum operator, because written in the angular momentum operator, the Schrodinger equation has a nice way of decoupling, okay, in terms of the radial coordinate and the angular coordinate. And we will discuss how to figure out the solutions of this equation starting the next lecture.